Hello, Royals. Let's take a look at lesson 5.1, the trig prerequisites. I want to start with walking you through some sketches and make sure that everybody knows the idea of framing your curve and stretching your scale instead of your curve. First example on the lesson is f of theta equals 2 times the cosine of pi times theta minus 1. I'm going to start by drawing myself a parent cosine curve. Here's my frame of my curve. A cosine curve, I usually start with the y-intercept or dependent intercept of 1. And we'll want to make sure that our curvature is appropriate. We'll be able to take a look at calculus skills applied to these curves. Make sure that you are inflecting on your axis points. So normally my axis of the curve would be y equals 0. This curve is not translated vertically, so it's still y equals 0. Normally my amplitude would be 1, so I would have a maximum of 1 and a minimum of 1. Instead of drawing the original curve and stretching it vertically by 2 and having a steeper curve to draw, I'm just going to stretch my scale. There, now the amplitude's 2. I can do the same with the period and the shift. Let me deal with the shift first. Normally, a cosine model would have a y-intercept that's a maximum or a maximum on the y-axis. This curve is going to be shifted right 1 unit, so I'm going to label that right there 1. Now that's 1 because I say so. And let's talk about the period. Our new period is going to be a horizontal stretch of our old or original period. My horizontal stretch is going to be the reciprocal of the absolute value of k. It's been a while since we've had to deal with transformations. So in this case, my new period is going to be 1 pi of my original period for a cosine curve would have been 2 pi, and 1 pi of 2 pi is going to be 2. Having the full period is useful, but I kind of like having the quarter period. Because this change in my independent variable is 1 full period, but I want to label these key points, and those occur quarter periods apart. So the quarter period in this case is going to be 1/2. And now instead of stretching my curve by a factor of 1 pi, which nobody wants to do, I'm just going to go forward 1/2 units and label these points. This is 2 halves. This will occur at 3 halves. This is 4 halves, also known as 2, 5 halves, 6 halves, also known as 3. And once I label the curve, there's my sketch. Okay. Let's try G over here. I'm going to draw a parent sine curve. Parent sine curve, I normally think of having a y-intercept of 0. Notice I'm not labeling my y-axis, and you'll see why in a bit. If I want to try to increase my accuracy of my curve, I could try marking the half period distance and the quarter period distances like that. Should keep it a little bit more symmetric. Pencil's a good idea. Okay. I want the axis of this curve to be y equals 3. Boom. Now it's y equals 3. I want the amplitude to be 1/2. What's this? 6 halves? That's 7 halves. 6 halves. This is 5 halves. Done. My let's see. Let's deal with the reflection first. Normally, a parent sine curve is on the rise out of the y-axis. I could try to reflect this curve down here, but why don't I just move where my y-axis is going to be and pretend that this is what I meant to do all along, that here's the y-axis and here's my curve coming down because it's been vertically reflected. So I'm going to label that right there 0. Or I could even draw in my y-axis there, my dependent axis. Now let's deal with this period. My new period is going to be 1/6 of my old period, which in this case was 2 pi. 1/6 of 2 pi is going to be pi by 3. Let's figure out the quarter period. That's going to be 1/4 of 1/3 of pi, also known as 1/12 of pi, or pi twelfths. So I'll just label, I didn't give you the specific directions. I think the intent was for us to sketch one cycle. of these two curves, but then for the cosine curve, we'll probably want more than one cycle. Yeah, let's just label these points. Going forward, pi by 12, there's 1 pi by 12, 2 pi by 12, also known as 1 pi by 6. And then this symmetry will make things a little bit easier. There's negative 1 pi by 12, negative 2 pi by 12, also known as negative 1 pi by 6. Notice that I'm labeling my independent values here on the, or in both cases, sorry, along the minimum axis. I feel like that's a good place to label them because they're out of the way. If I was labeling, say, my independent axis in the first example, then those, I feel like my curve would get in the way, or the labels would get in the way of the curve. Over here, I haven't even drawn the independent axis. You could put it down here if you want to, but I don't think it would add anything to your understanding of the curve. All right. Let's just review a parent tangent curve. I'm going to slide down a bit here. I think I labeled the last one, or named the last one, h of theta equals the tangent of theta. Most important thing to recall about the tangent curve is that its original period is shorter. It is pi. It also doesn't have an amplitude. It's not sinusoidal, but it is periodic. It does have an axis of the curve, and just like for sine curves and cosine curves, where they inflect along the axis, the tangent curve also inflects along the axis. The tangent of 0 is 0. The tangent of pi by 2 does not exist as theta approaches pi by 2 from values that are less than pi by 2. The tangent of theta increases without bound. So I have an asymptote at pi by 2. There's 0. Then I can use my understanding of the tangent ratio as being the ratio of y to x to figure out where the tangent curve is positive and negative. We'll discover that the tangent curve is never horizontal. It's not the best curve that I've drawn. There is an inflection point there, but it is not a stationary point or a critical point. It is a root, I suppose. And that happens at 2 pi by 2, also known as pi. And then I can sketch from here, and there's me deciding to stop at 2 pi. I might put a little bit of a tail on it there and there, so my reader understands that it does continue forever. From left to right. Oops, let's label that 3 pi by 2. How's that? Okay, next on the list, there are a bunch of identities to look at, and I'll ask you to practice proving an identity, I think, in the homework, and perhaps manipulate these compound and double angle formula. You don't have to have them all memorized. Having one or two memorized should help you develop the others if you need them. It will be useful once in a while to simplify expressions before differentiating. I've got a couple of examples that I want to look at where we're solving. I would say that solving trig equations is one of the most important prerequisite skills. So I want to practice those questions on the second page of this lesson. Just give me a sec to get those set up here. Let's try solving over a fixed interval from 0 to 2 pi. And I think the first example we're given is 4 times sine of x multiplied by the cosine of x. There are solutions on the lesson, but I wanted to sort of explain our way through this. I believe the lesson says that our goal is to try to use identities to find equations with one ratio on one angle per factor. So this is where those double angle formulas will come in handy. I can't really try to isolate a sine of x or a cosine of x here. If I didn't have this minus 1, it would be a little bit easier because then I could just say either the sine of x is 0 or the cosine of x is 0. I have two ratios in the same factor. So what I'm going to try to do is look for an opportunity to use a double angle formula. And the double angle sine formula is one of the most useful. I would recommend seeing if you could get that one memorized, because it does allow me to replace multiple ratios with one single ratio. Sometimes students call this a double angle, but I want to make sure we understand it is still one angle. Whoops. So that the double angle being a single angle, you can see sort of the trouble with that language. Okay, now I'm going to use linear skills to try to isolate 2x. I'll add 1 to both sides, divide both sides by 2. That'll give me the sine of 2x. will equal 1/2. I shouldn't need a calculator to do this one. I should recognize at least one solution here is going to be exactly pi by 6. That's a solution for 2x. 2x could be pi by 6. A couple of different ways to get this second solution here, the multiple solutions. A lot of students like to use standard position to find the two values for 2x. That's not really going to help you find the third and the fourth solution, though. So why don't I just finish this one up here and say that x could be, I multiply both sides by 1/2 pi by 12. And what I'll do instead that I didn't show on the lesson is use a curve to solve. And I think the curve that I'm going to use is probably from right here. I'm going to set this to f. I'm going to sketch a sine curve that has a period of pi. Like that. So there's 0, there's pi. And either my calculator or my understanding of trig ratios has given me this first solution right here of when am I at a height of 1/2. Well, that happens for the first time right here at pi by 12. So here's where my curve comes in handy. Sometimes grade 11 students memorize that, oh, you do 180 degrees minus this answer to get the second answer, and that's not the case here. I want to go back this distance of pi by 12 from an axis point. Because of the change in my period, my axis point now happens at pi by 2. So I'm going to label this x sub 1 because it's my first solution, and I'll communicate to my reader that my second solution is going to be given by pi by 2 minus pi by 12. Let's see, that's 6 pi by 12 minus 1 pi by 12, 5 pi by 12. Okay. Without showing the sketch, the labeled sketch, all the way from 0 to 2 pi, I think I should be able to reason that the next solution is going to happen one period later. I like to call these symmetric solutions, and then x3 and x4 periodic solutions. They happen not because of symmetry, but because of the period. So I could, without being too specific here, say x3 is going to be x1 plus whatever the new period is. Specifically in this case, I'll say that's going to be pi by 12 plus, what was my new period? Pi? I should probably write that down somewhere. So pi by 12 plus 12 pi by 12, that'll be 13 pi by 12. x4 is going to be x2 plus one new period. That's going to be 5 pi by 12 plus pi, or plus 12 pi by 12. That's 17 pi by 12. And there are my 4 solutions. Try that out with the other 2 equations, using sketches to visualize things. For the third example, where I end up building a tangent ratio, I don't have as much experience sketching the tangent curve, and I'm not sure that the tangent curve is a great way to visualize multiple solutions. So if you end up just solving in standard position, that's not going to be a problem. Give that a shot.